Polynomials are infinitely differentiable. This fun property can lead us to an interesting result, that the nth derivative of a polynomial p is equal to its leading coefficient multiplied by n factorial, which can be concisely written. Recognize that this product is a constant. Before we actually obtain this equality, it would first be sensible to rationalize the idea that the repeated derivation of p will eventually lead to a constant function. First, we can define a polynomial p as an algebraic expression with variables and coefficients of the following form. The degree, n, sits in the set n0. This is the set of the natural numbers, but also including 0. Notice that our leading coefficient is an, and that the coefficients are not necessarily real valued. Any coefficient, ai, is complex, which makes our final result even more fun. It can also be helpful to view a polynomial from an alternative viewpoint. We can see a polynomial as a finite sum of monomials, where a monomial is a function of the form ax to the n. It then becomes an intuitive step to write a general polynomial as the sum from 0 to n of akx to the power of k, which of course expands and simplifies to equal our first definition. In order to convince ourselves that under repeated derivation, polynomials eventually become constant functions, we must make two simple observations. First, differentiating a constant makes it disappear. This is because the derivative describes the rate of change of a function, and constant functions are constant, they don't change. Then the constant function f equals c has the derivative f prime equals 0. This can be formalized in Leibniz notation by writing dc over dx equals 0. Second, if we look at the derivatives of monomials, we can see that the exponent decreases by 1 after each derivation. This is commonly known as the power rule. d over dx, ax to the n, equals anx to the n minus 1. Notice that the degree has gone from n to n minus 1, implying that under n repetitions, the exponent of x will become n minus n, which equals 0, and we will be left with some constant c as the coefficient. Therefore, the monomial will transform into a constant function. With these two rules, we are prepared to observe a polynomial under derivation. Let's make some space. The general polynomial p of x can be written as defined earlier, with degree n and n plus 1 terms. Take the first derivative of p. Due to our first rule, the constant term a0 disappeared under derivation. Because of the power rule, the degree decreased by 1, and notice we now have n terms. The leading coefficient becomes an multiplied by n, and it is apparent that because of the second rule, there now exists a new constant a1. When we differentiate for the second time, the first rule ensures that the new constant a1 disappears. The power rule decreases the degree to n minus 2, and the polynomial now has n minus 1 terms. The leading coefficient becomes an multiplied by n minus 1, and the second rule creates a new constant, 2a2. There are many patterns at play here. Notably, after each derivation, we lose a constant term because of the first rule, and we create another constant term because of the second rule. It then becomes intuitive to see that if we repeat this process n times, the nth derivative of p will have just one term, as n plus 1 minus n equals 1. The variable of this polynomial will have a degree of n minus n, which equals 0, and therefore be a constant function. We can write the nth derivative of p as such. This is because the pattern of leading coefficients under derivation ensures that the final product is equal to an multiplied by all values n through 1, which is equal to an multiplied by n factorial. And we're now finished. We have understood and shown why this fun result exists.